If the reaction is second order with respect to the concentration of nitrogen and first order with respect to the concentration of hydrogen, calculate the rate constant, write the rate law, and state the overall order. In the question that I just showed you, we're told that nitrogen reacts with 3 hydrogen to give us 2 ammonia. In the body of the question, it also tells us that the reaction is second order with respect to the concentration of N2 and first order with respect to the concentration of H2. The question asks us to calculate the rate constant, to write the rate law, and to determine the overall order. So here is the generic form of the rate law from your formula page. Rate is equal to the rate constant, little k, times the concentration of the first reactant, raised to the power of its coefficient x, its order, multiplied by the concentration of the second reactant, b, raised to the power of its coefficient or order, represented with a y. If there were a third reactant, we would continue with the third term, c, and its order, and so on. So the first thing is to calculate the rate constant, to put in the orders and the actual reactants. So we can say that the rate is equal to the rate constant, little k. A, the first reactant, is N2 gas, and its exponent or order, we're told from the question, is 2. B is the second reactant. Remember, where this operator isn't shown, it's multiplication. B is hydrogen, and its order is 1. So you'll notice that these, unlike our equilibrium constant, have nothing to do with the stoichiometric coefficients in the reaction. They're determined from experimental data, or for technologists, you'll be told what the order is. Our next step is to return to the question to find a set of data. You can use any experiment, experiment 1, 2, or 3 from that table, as long as all the values are from the same line, from the same experiment. I'm going to choose experiment 1 because the numbers look fairly easy. I'm going to fill in the rate, the concentration of the N2, and the concentration of the H2, which will leave me with one unknown, K. And once I figure out the rate constant, I can rewrite this whole thing with the rate constant included. So from the first line of data, the rate there is 4.0 times 10 to the negative 5, and the units of rate are always molar, moles per liter, per second. The concentration of the N2 from that line of data is 0.100 molar, or moles per liter, and that's squared. The concentration of the H2 is also 0.100 molar. And now all we have is one unknown, K, and we just need to use our algebra skills, rearrange and solve. So 4.0 times 10 to the negative 5 mole per liter per second is K. And when I square this and multiply this, I will have 1.00 times 10 to the negative 3 mole per liter, or molar cubed. So you see, there's no reason to use square brackets anymore. Up here it means concentration of, but once I've substituted mathematical values, you can use square brackets, but you don't need to. To get K on its own, we're going to divide each side by 1.00 times 10 to the negative 3 molar cubed. And I can say that K is equal to 4.0 sig figs times 10 to the negative 2 mole per liter to the minus 2 seconds to minus 1. So a little observation for you. It goes hand in hand with the next question, the overall order. The exponent on moles per liter in the unit of K will be one less than the overall order of the reaction. Let's just put this K back into the rate law. Rate is equal to little k, but here I'm going to actually put the value of little k into the rate law. 4.0 times 10 to the negative 2 mole per liter to the minus 2 seconds to the minus 1. Multiplied by the concentration of N2 gas squared and multiplied by the concentration of H2 gas to the first power, and of course you don't have to write the exponent 1 if you don't want to. The overall order is the sum of the individual orders, so the overall order here is 2 plus 1 or 3. And a little observation for you, seconds to the minus 1 is always going to be in the unit of K. The unit of mole per liter will always be one less than the overall order multiplied by negative 1. So 1 less than the overall order, so 2, and then times negative 1, it'll be negative 2. And that is in fact what we got. In part 2, we're asked, what is the rate of reaction when the concentration of N2 gas is 0.30 molar and the concentration of the hydrogen gas is 0.40 molar? The next part of the question asks us to calculate the rate using the rate law if the concentrations of nitrogen are 0.30 molar and hydrogen at 0.40 molar. So all I do is take the rate law, which I wrote in the last part, substitute these values for nitrogen and hydrogen, and work out an answer. I should see my units of my rate constant come out to be molar per second. So rate is 4.0 times 10 to the negative 2 mole per liter to the minus 2 seconds to the minus 1. The concentration of the nitrogen 0.30 molar squared and the hydrogen 0.40 molar to the first power. So I get 1.4, don't forget the operation here is multiplication. 1.4 times 10 to the negative 3. My unit's mole per liter squared, mole times mole per liter is mole per liter cubed, and then times negative 2 will give me moles per liter to the positive 1. So mole per liter per second, which is exactly what I was expecting. 1.4 times 10 to the negative 3 molar per second.